All right, we are seemingly live. I'm back in California. I have a lot of new equipment. I have a microphone. I also have a nice camera. We're gonna try to figure out how we can get this to be very nice because we want it to be like mounted, and then I'll put something on the background to make it nice. We'll get into that in a second, but I want to show another thing that is very freaking cool, and that is this. Well, hold on. This, which is a digital oscilloscope, and it also has a function generator, and so it's pretty cool. It's a nice little device. I just got it set up, so let's jump into that. This thing called waveforms, and you can see I don't have any of the probes attached, so it's an whatever. But if we just run it, we can see that there is some signal. If I oh, this auto thing is kind of interesting. Yeah, if we turn off, let's try to turn off auto. Oh, and see this spectrogram? Oh, let's look at this 3D spectrogram. You think I'll be doing that. That is pretty neat. A 3D spectrum. What even are the axes? Dude, this is a really cool piece of software. Okay, so we have amplitude. I don't know why there's two amplitudes. Then we have frequency, I guess. That's pretty neat. So we can close these things. I don't actually know what this XY thing is. Okay, so we can pause this now. So that's pretty sweet. I think it's about time that we... Okay. I really want like a nice, like Moritz Klein has really nice overhead views when he does breadboarding. So I'm wondering how I'm gonna do that. I feel like I could just get a box and put it to my side. Maybe I'll go look for a box. The thing is, this is a nice tripod. So let's turn it on. This is just not nearly as nice, though. Off center, it really, like, the benefit is you want it to be, like, centered. You want it to look nice. And then we also don't want anything in the background. So I feel like a piece of cardboard might be fine. What does he have? He uses this like concrete surface, which is really nice. I could use the white table, but I'm not sure. But the camera angle is definitely the most important thing. So I might just get some tape and a box, put it like a pole, like this, and then just clamp it down like that. Alright, that's what I'll do, I guess. Yeah, and I'll tape it on this side of it. Okay. So let's go in search of a box. Okay, we found some boxes. That's pretty cool. So I think I'm gonna do, the thing is, I wonder if I can, I almost certainly can just unscrew this, but maybe I don't want to. Fuck. Okay, no tripod. And then we have some room here. Well, not really, though. See, if we stand the box up like this, that's pretty good. It just doesn't give me a lot of working room. Whereas with the tripod, I could do all the way out to here. Hold on. I could go way out to here. All right. Well, let's see what we can do about this. First thing I'm gonna do, I'm gonna tape this thing back up. Oh shit! How do you even? Okay. Actually, I think you can just rip duct tape. Nice. Okay, we have a box, which is our jank camera mount, and then I'm just gonna tape it down, I think. I think I'm gonna apply the RNN filter. Hold on, I'll show you guys. Yeah, see, it's trash day here, so it's like brutal. But if we do this and this, hello? That looks pretty good to me. Okay, so now we want this mounted here. Move this back. I don't know. We probably don't want this to leave a residue. It's probably fine. All right, let's just do it. Fuck it. Dude, this duct tape is sweet. We're gonna see. This is probably not that sturdy. Oh, tape. It will be worth it though. For good quality shots. The problem is we don't want wobble. We really don't want wobble. Okay, well, let's test it. So let's screw this back in. Yeah, it's pretty annoying. Maybe there's like a stabilization thing I could apply. I don't know. Especially if it's out here and I bump it. You know what, but I think that's fine. I mean, that looks pretty cool. I used to, in college, I used to have this thing that would, there was like a metal grate above my desk, and I would like clamp it because it was like a rubber thing. Okay, so let's just do this thing. Shit. Okay. Hold it down. Okay, we don't need this. So we want this to be here. Okay, then we'll do the cross. The nice thing about this though was that I could move it around. I guess I could detach it, but unscrewing it's kind of a pain. But you know what? It's good enough right now. It's so much better than my previous breadboard sets. Let's add one more piece of tape. Really make it in there. Oops. That's really locked down. This is about what wobble we can expect, which I'm pretty fine with. Now we just need to cut out one of the sides of this box and use that as our background. I think on the inside it's blank, so we'll use the inside of it. Okay. Alright, so let's see how that is. And what we could do is we could tape two of the bigger ones together so we don't have this crease, but for right now I think it's fine. Okay, so now this is our makeshift electronics set. And we get us a nudge it in there. We want the full shot, so we can't move that. We just have to do this. Center it. That's pretty good. All right, so today we are building a voltage-controlled oscillator with a couple of parts. We are going to need we're going to need a TL074 or an 84, I don't think it really matters, but we're going to need some op amps. And yeah, the noise floor is pretty good. And we are going to need some Schmidt triggers, some IC. So for right now, I think is there a copy paste? Oh, there is a duplicate. Okay. Well, anyways, let's turn this off for right now, and we'll pull up the schematic. I actually have it. Let's see. Put this here just so that no one can. Okay. Oh, shit. It's okay. Okay, we're following this. This is the schematic. And the bill of materials. All of this can be found on his channel. I'm just going to be doing the walkthrough, and we're going to be doing it on a breadboard, but then I actually have some strip board, which eventually we're going to, by the end of the week, hopefully have a box that we can actually put our synth modules in, so we'll have a full thing. Having a second monitor out here would be helpful so that I could keep tabs on the stream. Okay, so yes. So the first part of this is we have two 9-volt batteries. Okay, now, hold on, I'll be back. Okay, I need to clean this up. Put this back in the garage, because I don't think we'll need it for a while. Okay, so where's my other battery? Okay. Two 9-volt batteries, clips. What I'm gonna do here is I'm just going to cut the heads off. We'll cut the heads off right about there. Wire strippers. We probably want to make these about equal length, so I'll do the first one. Oh wait, gotta make use of this thing. Okay, so we have our thing. I'll give it some room on both sides so that you could solder it back together if you needed to, because cutting it here is stupid, because then you can't use it. And this side, the male side, is destroyed. Okay, then we'll strip this wire in a second. But first, what we want to do, line these up. Oh, this one's longer than the other one. Okay. That's fine. I bought more anyways. Okay, so now we have these two things. This is junk to me right now because I don't have anything. Now we're going to pull them apart if I can. There we go. Okay. And then let's find the right size for these. They're probably less than 22, but there we go. Let's see. Oh, no. That's really annoying, actually. They're not solid. That's really annoying. I feel like we could probably quickly solder. I found this thing, and in it are these gold-plated pins or whatever. Oh, I'm gonna have to get used to the focus on my hand. Anyways, okay, so I think I'm gonna have to do that because these fit in here really nicely. So maybe we'll have to go get the soldering iron. This isn't how you're supposed to do it, but you know what? I don't give a shit. Speaking of, I'm gonna quickly I need a scene. Yeah. I need a scene that's just black. So let's just rename to blank. Okay, I'm back. We are making a DIY synth, and where we are at is that these clips that I found have non-solid core wire, which is really fucking annoying. But it's fine. We'll strip off some more of this so that we can solder to it. I was hoping to not break out the soldering iron so soon into this because whatever. But I guess to make this thing work, we could either do this or we could wait 10 hours because I bought some. But there's just no way in hell I'm waiting. Okay, so off to the basement. Not many people have the luxury of soldering outside. I had some heat shrink tubing, it would be even better. All right, so we need some aesthetic shots. So we need 1, 2, 3, 4 of these. And we're going to see how this goes. Let's clear our space. The only problem is this iron doesn't have a temperature sensor, but that's fine. And then we are going to use a fan because I'm paranoid about lead solder, but that's all I have right now. Okay, so we don't need the scope at all. Cable management. Move that. This here. Oh God, this can't be. Oh God, this can't be. I mean, we're outside, but I still don't care. Oh no, but that's destroying the microphone quality, unfortunately. So we're gonna put this here. Move this here. Okay, we're gonna turn on the soldering iron. All right, we are all good. Wow, this is really thick solder. I need to close the door. Hold on. I've been dreaming of someone making an OBS where you transmit way more data. You transmit all sources in full quality and microphones, and the compositing gets to be done by the user. Like, it'd be so useful if you wanted to zoom in on this shot and didn't want to see my face, then you could just turn off my face. But what I can do actually is, yeah, so now this is in front and I could do this. I want to show people that I'm outside, but maybe I could crop it. All right, so let's move it back down. I think it was good how it was. And we could just make it a little bigger. Move me over here. That seems pretty good. And then the chat, that's nice. Okay, cool. So the soldering iron is probably up to temp or close to. We're going to see how this goes. Nice. Ooh, I wish I had a zoom control. I wish this thing had like a physical zoom button. Okay, but you can see here, this first contact is pretty strong. Damn, it doesn't focus well either. But whatever. Okay, now let's do the second one. Oh shit, that was not a good contact. Need to add some more solder. Okay, used too much solder, but it's alright. I also don't have a sponge, which would be kind of handy right now. How am I going to do this? I need it to be on the, let's hold it down with this battery. Is that visible? That is sort of visible. Okay. Good, good, good. Okay, then I think we want to flip it over again. Because this one's not going anywhere, but if we don't flip it over, it's going to be a problem. Okay, we're almost done with this, and we can power our breadboard with a dual power supply using 9-volt batteries. Pretty neat, eh? Oh, this lead solder is actually so easy to use. It's kind of crazy. It just really gets on there. So now for demonstration, instead of using this stupid wire, we can just go like this and like this. And unfortunately, you can see potentially this is awfully close to being contacted. So what we're gonna need to do, separate them out. We need to do something silly like this goes into here. This goes down here. This is only temporary though, so it's okay. Okay, and now let's do the second one. Okay, here we exposed a lot of oh, this solder is so nice, it's crazy. I kind of feel like an idiot for preferring unleaded solder. Hold on, I gotta twist it up. Twist it up, twist it up. Okay, so we still need to do this side of this one. Okay, that looks good. And then our last pin here. Seems fine. Shit. Okay, that's pretty good. We just need to do a little bit more. All right, cool. So we're done. Now we want to, where's my multimeter? Now we want to do the tests. We can turn this thing off. It's freezing my hands. Okay, so we're clipping our batteries on. So this one, so that one, now we want this one to go here, like, oh shit, the wire's so weak, I feel like This is a 1-day thing max, because this is just so shitty. Oh yeah, we gotta clean this crap off of here. Oh, this is horrible. Maybe I should have just used alligator clips, but it's so ugly. Okay. So now what we want to do is we want to measure. Okay, so we're clipped together. Now we want to measure from. Okay, we'll just measure all of it. This is a pretty aesthetic shot, I think. Okay, so now we are going to measure. Where's the DC voltage though? Does this just do both? Okay, well, let's just do a simple continuity test. Hmm. What's up with this thing? So I'm not getting a reading. I don't know what's up with this thing. I mean, it seems to be working, but the screen... Okay, so I'm gonna go grab another one, I guess. And put that one away. Might as well put the soldering iron away, too. No, we might need it. Okay, multimeter number 2, because I don't know what's up with this one. Okay, so let's check. The reading is not all that readable. That's okay. Doesn't have to be readable by you, does it? It just has to be readable by me. Okay. 9.53. Shit. Minus 9.58. So now if we do this, wait, so which one? So we put the black terminal here, so this should be minus 9. If we go from there to there, we get minus 9. And from here to here, we get 9. Yep. Okay, so then these are grounded. Now we just get to start stripping lots of wire. So let's first put the ICs in. So here's our Schmidt triggers. Looks like he puts it in at 21. Sometimes you have to bend the leads of these things a little bit to get them in the breadboard. So we'll see about that. Let's move this crap. We need a trash can. That's what we need. Okay, for now, I'll just put this here. Yeah, we're definitely going to need a trash can. Okay, so we're going to put it in at 21, facing upwards. So actually, we had this backwards. Okay. 21. Fits right in. Okay, now we need to ground everything. So I'm going to take these probes out. God, I hate these things. Should have used alligator. Okay, so now we just need to make a shit ton of wire. So let me get my wire and a trash can. Wire. Don't need any more of these. So let's put this back here. Yeah, okay, what should I get for a trash can? That's the push. All right. Now we have a trash can, which I will. This has to be here. I'll put it because I don't need my multimeter, especially not the broken one. The soldering iron can go too. Okay. So now we just need to ground all the inputs to it so that we don't have noise, because otherwise it'll draw power and random things like that. Okay. I think this is 22 gauge wire. Oh, these wire strippers are really nice. Wow, that was fantastic. Mine at home are trash. These just snap it off, man. That's something special. Okay, so that is its power, but then it starts its inputs on pin 2 over here. So we put this in. Okay, I need to remember. Throw away all of the little bits of plastic. I don't want to make this outdoors messy. This beautiful outdoors. Wow, these wire strippers are so nice. It's crazy. Mine at home, I'm like fighting it constantly. Nope, that's not right. Okay. Grounded, grounded. This one needs to go to, it's too short. Wow, this makes life so enjoyable to have nice, sharp cutters. This can't be. It's the second to last. I always mess that up. Okay. Cool beans. Now we need, yeah, 2 more. This is just the boring part, so there are going to be boring parts. So let's just get it done. Ooh, we probably want less than that. This might be too short. It's pin 1 on this side. Nope, perfect. Never mind, I don't like it. Okay. Okay, so that's very nice. We have everything grounded. We need the diode, and we need a capacitor. What diode does he want? So it's yeah, this one. Okay, I have that. Mr. Diode. Okay, so now that we've grounded all but one of the Schmidt trigger inputs, we will build the oscillator core, which is basically just this. You have the input to a Schmidt trigger tied to a capacitor and a resistor in parallel to ground. Okay, these are the diodes. Then I have a resistor pack here, which I might need to go get more, but I found this just lying around, so I figured probably has most of what I need. And there we go, 100K resistors. Perfect. The problem is the capacitors are in this big, all these freaking cringy electrical engineers are like, "Oh, we're gonna do it out. We're gonna do it inside." I don't think that way, bro. I say, get me outside. Get me outside. Get me outside. Yeah, that's okay. All right, so this one goes to ground. Like, oh, and I like these resistors. They're thick. There's not many in there. There's only, what is that, 10? But so we'll run out of those quickly, but I'll use them when I have them. And then with the diode, we'll grab one of these diodes. Does he say what type of diode? Signal diode. Okay, and then the diode is going from, the diode is blocking, where's the picture? Okay, there's the pinout, that's nice. So the input is there, and we want to block current from flowing from the output to the, or from the input to the output, right. We want to block current from flowing from the input to the output. So then that means that the diode is going to face this way. And you can always tell, well, pretty much all the time, which way the diode is by a little line that's printed onto it. Okay, that's very nice. Now we need our capacitor. I have to think about that. But then once we're, oh, and we need to power this thing. These wire strippers, I'm not going to stop talking about. They're giving me life. Okay, we have successfully built the oscillator core minus the capacitor. Okay, so it's a 2.2 nanofarad. All right, I will be back. . Okay, that took a long time. And what that means for me is I'm going to hop over to Blank, and I'm going to buy some stuff from Amazon. I'm going to buy that capacitor kit. Okay, I'm going to buy this thing. And I'm going to get also we'll see if I need the electrolytic ones. I don't know if I do. I probably do, but I'll get that kit later. And then I need a lead-free solder. And then we just go to proceed to checkout. And we buy it. Amazon is so sick. Cool. Okay, so now I bought a capacitor kit because I didn't see any. I found this 2 nanofarad one, but it's like from the Stone Ages. You know what I mean? We've gotten better at manufacturing, man. Plus, I think that this will destroy my breadboard a little bit. But right now, the goal of this stream is we want to test out. Okay, no, they fit in nicely. We want to test out this super cool oscilloscope because I've never used it really. Okay, so now what we need to do is we want to check that if we take our batteries, that because we can't supply 18 volts to this thing or we'll fry it. So we need to make sure that the grounds are correct. Okay, so this one is set up like normal and the other one is flipped. Okay, and then let's get our guy here. And then I'm going to make a small wire to measure. Oh, and do we have to bridge? Do we have to connect? Yeah, we probably do. Okay, so this one will just be for measuring. That's too short. Yeah, so this one will just be so that we can connect our probe to ground here. And then we want to measure the input to the Schmidt trigger, which is here. And then we want to bridge grounds. Then we should see plus to plus. Let's see, how long do we want that? Maybe like there. I'll probably end the stream once. It's too short. Well, maybe not. Oh, I should have gotten some needle nose while I was down there. Yeah, too short. Okay, cool. So now if we measure, so it's, oh wait, but we, oh, the sun. I'm so excited. Shoot, I didn't think about this. Should we just try it? Is this thing running? Okay, so now we need to adjust scene. Okay, so this is, we're gonna rename this to overhead. Then we need another one, which is gonna be overhead, small, or window and small overhead. So then this is going to be, can we just copy this? Nice, that is sick. And then we just want to put this above me. We can put our diodes away. And put our resistors away for now. Yeah, I'm getting hungry, so I don't really want to say fuck it though. Right, because the difference between here and here. Right. Okay, I think I'm ready to say fuck it. This thing makes sense to me. So what I want to do is I want to go over to waveforms. I want to run it. Is it running? All right, so it's going. So now we want to switch this. Here and there. Okay, but then we want to put the black into plus here. The red into... So is that working? I don't know. I don't know if that's working. It seems like it is. Can we, how do we... I want auto. I mean, it seems like it's oscillating, but it's oscillating so small. Range 500 millivolts? I don't know. Can we make it 50? I mean, that looks pretty good. Oops. I mean, this is a pretty good indication that it is working, right? Like, it would be dead otherwise. Cool. So we successfully built the oscillator core. Unfortunately, I might need to go scrounge around for a speaker, but we can't listen to it yet anyways, because we need to buffer it. So why don't we add the buffer? So we're gonna add the op amp and the AC coupling, and then we can be on our merry way. Okay, so we have, so wait, now we want to switch to big overhead. I mean, we can stop this, and we can actually take it off. So that was very cool. It only took us a couple hours to we don't need, well, we are gonna need wire, so I'll keep this here. And then we should not power this anymore. So now we're not powering it anymore because we don't want to do anything silly. I'll probably need to buy more op amps, but whatever. Who is that? I don't even have that. Oh, it's... I want to disconnect this. I don't like this. I don't want anyone reading my text messages on my computer. I need to go get my phone battery. Alright. Anyways, so we have these. TL074. Oh, wait. I missed one. Okay. So now we need to... I wish it was slightly more zoomed. I wonder if I can... What if I did this? Nope. I hate that. I gotta stop messing around with this stuff. Alright, that's pretty good. Okay, so now we actually do want window, and we want to add the TL074 at 30. Okay, so see these TL074s, they make the legs kind of wide, so we need to push them in a little bit. Just ever so slightly. Okay, and then this one faces down. Okay, are we all good? I hate bending the pins on ICs. Okay, nice. That fit in good. There's only 2 spaces between it. Alright, nice. So we should power it. Ooh. That's no good. We do not want these leads to short. I mean, it's not the worst thing in the world, but it's just annoying. Okay, so now we can switch to overhead. And I'm just going to power this. Okay, so this one, this is kind of long, so we'll do this guy over here. Okay. Very nice. So now we've powered it, and we need a buffer. So we need a short one. These short ones are really hard to do, but these wire strippers, oh, these wire strippers are to die for. I still think this might not work, but we're gonna see. Yeah, I don't think so. Okay. throw that away. It needs to have like basically no shielding, pretty much. Okay, that should be good. That is pretty good. Okay, now we have the buffer. Now we need to send the oscillator, yeah, to the buffer. So that's okay. I'll take a little more off. That's too much. Okay, and then we're sending that down there. Okay, so this goes from 25 down to the input of the non-inverting input to the up amp. What the heck is going on here? Come on, get in there. There we go. And then the output goes to this AC coupling, which is easy. Need 1 microfarad, so I'll have to go find that guy. And then another 100 ohm resistor to ground. 100k ohm resistor to ground. And then we don't have any audio jacks, so I probably should order some of those. I want the nice ones that he has, but whatever. So that's at 41. Okay, we'll get the resistor in a second. And then we're going to look at it on the scope, and I'm going to get some food. I'm going to cook it up, cook it up, cook it up. That's probably long enough. Oh, shoot. Okay. Then we send this guy all the way down to 39. Okay, now we just need the capacitor, and then right. What else do we need? We need yeah, now we just okay, now I get the capacitor, and then we'll hook. Okay, yeah, I get it. Okay, so it appears that we do not have so time to go to Amazon again. Time to get some electrolytic capacitors. Okay, cool. All right, I just bought some electrolytic capacitors. All right, but I think that we don't need that. I should have looked for the speaker while I was down there. Speaking of, okay. I mean, we don't technically need a 1 microfarad, but you could use something, whatever. I could divide it down and record it into my DAW. But I think I'm going to wrap this one up. Oh, shoot, I forgot. Okay, so what did we do? Well, this is nothing. We could just listen to the output there. Why not do that? I'm done with that. So we should see the exact same thing as we had before, except now it's buffered by the op amp. So this goes here. Black wire is obviously stupid for this. So now we can go to window and small overhead. We can run. And so now we get noise. But now we're going to plug this in. So we're going to start powering. And then here we reverse it so that the positive terminal goes to negative and the negative terminal goes to positive. And we're seeing nothing. Why is that? Hopefully we know fry it. Oh, that's not good. Oh, wait. Oh, it got hot. I definitely destroyed this thing. Oh, because I put it in backwards. Okay, let's see. All right. That's unfortunate. This thing is definitely dead. Oh, never mind. Okay, cool. So now let's try to listen to the buffer's output. And we have the same thing. And it's okay, so now I want to add a voltage divider. I don't know, how much gain do we want? $1K and $2K. Let's do that. For I always do this wrong. Voltage divider math. Right, it's R2 over R1. So it should be 2 over 3. Okay, so if we connect, and I always forget how to do this. All we have to do is, instead of using a buffer, so what I'll do is I'll send this to the input, to a non-inverting input of this buffer. How small is that? It's not the worst thing, but it's not good. Oh wait, this is still being powered. Take these guys out. Okay. And then what we're going to do is have shit. Okay. We're gonna have a 1K a 1K that connects the input and the output, and then okay, I think that this will work. And if it doesn't, it doesn't. But it's so, I feel like when I started doing this like a couple weeks ago, I was like so scared to break everything all the time. And at this point, I'm like, all right, you know what? I just kind of want it to work. I want to try it. Is that fucking in there? Yeah, it is. Okay. So this is the 1K, and then I think we want the inverting input to also have the ground. Yeah, because we can't tie the output to ground, duh. So we're going to put this 2K. And then if we measure the op amp's output, we should see it be 1.3 times louder. So I'm going to tie that to ground. Okay, we're in there. Okay, that's in there. Okay, now we change this to be that. And then we plug this in. We go to our... This is still running. We should probably turn that off. But whatever. Let's see what's going on. Okay, is it louder? I don't think it is. Let's see, what else do we have in here? What is the math again? R2 over R1 plus R2. So if we increase R1, okay, so let's put a 2K in there then. Let's unplug. Is this shorting? No. So we put this there. Then instead of the 1K, we put a 2K. And I wonder, does this waveforms thing, does this show a peak to peak somewhere? Can I get a peak to peak? It must say peak to peak somewhere. Like, okay, well, whatever. So we're going to unplug the 1K resistor. And we're going to put in a 2K resistor. And so this should be R2 over R1 plus R2. So it's going to be 1/2. So since they're of equal resistance. This in plus, put this in minus. It seems to be clipping. I don't like that it doesn't show. Like, so I guess it didn't do it. I don't like that it's so fast. Like, why can't it lock onto it? Okay, well, whatever. Be that as it may. The amplification didn't do what I wanted it to. But that's all right. Oh, let's stop this thing. Probably chews through a lot of CPU. Okay, so anyways, that's the first part of the oscillator. In a second, we'll change the pitch. I'm gonna go look for a small speaker or like amplified speakers that I could use with this thing. I don't know why the amplification didn't work. That should be how it is. But oh well. I don't think it's gonna rain, but I'm worried about it. Okay. Maybe I won't stop the stream and I'll just make some food right now. Alright, that sounds good. Yeah, I don't know why this amplification didn't work. At least we see a sawtooth. Let me I should do a recording. Let's do a simple recording. But instead of this, we'll put this, we'll just do this. Then we'll put this to ground. We'll unclip this and put this onto here. And then I'll click run. And we'll plug these guys in. And then we'll do chord. Channel 2. Oh. It's a binary file? Oh, I can save it as a wave. Oh, that's sick. We should do it at 50 kilohertz. Alright, and then should we save 20 seconds? We should only save, let's just save 2 seconds. Okay, cool. Dude, this thing is fucking rad. It's done, right? Oh. Okay, wait. It was in documents, though? Default.wav. Wait, hold on. I wanna... Let's see. Let's go to ChatGPT. Let's unplug this because we already recorded our sample. We're gonna see what's up in a minute. Dude, this thing is so freaking cool that you can just record. I love it. Can we see the spectrogram? Oh, actually, yeah, hold on. Can we get this? Plug it back in and record. I want to look at the spectrogram. We should see what's going on. Why is it so noisy? Oh, wait, did I change the sample rate? Yeah, we don't want this sample rate to be so low. But the audio being that, look at all the noise though. We don't like that. How do I change the sample rate? Well, I know how to do it from here. Let's go back to 10, what was it, 100 megahertz? No, what the fuck is this doing? No, but what is going on here? Settings. No. I think if I oh wait, I'm an idiot. Yeah, I'm an idiot. Hold on. No, I wanted to change this rate to be whatever 50 megahertz. That's fine. So now I think if we go back here, we run. Oh, and the trigger is fixed. Oh, sweet. Okay. Dude, this software is so cool. Tell me that oh, dude, I'm retarded. Okay, well, anyways, I've been using waveforms and it is pretty cool. Oh, the trigger's in some weird loop now. What did I do? Oh, there we go. The trigger got fucked. Damn. Literally, it's trying to keep on. It should be good, though. I don't know why it's not that good. Maybe we could just do none. Normal? What if we turn down the sample rate to like 10 megahertz? That is a clean signal. Where do I see the peak to peak though? That's what I do not understand. And where's this thing? What is this? No. See, that's the problem. I don't know. I feel like we're not seeing. Come on, go back to auto. We should see a massive peak. Can I get this in hertz, bruh? Oh. No, but the volume I don't care about, but the... We should see a massive peak, though. Fuck. Turn off the trigger. None. Okay, that's nice. It's trying to do too much. I don't know. Oh, we need the trigger, huh? What happened? Why is this back down? This is what's nice about having the knobs, I think. Alright, let's turn this off, because this isn't helping me at all. And then let's fix this trigger to auto. Nah, something's wrong. What's going wrong? No, I think it's just the sample rate. I don't know why it changed the sample rate on me. You're not allowed to change the sample rate, buddy. Maybe it's too high frequency. If we lower the I think if we lower the resistance to ground, then the frequency gets higher. So we need to increase it. Okay, so we want to zoom in though. Show entire capture thumbnail. I mean, it absolutely should be able to clock into this thing. Mode repeated. Let's bump it up to alright. I don't really know how to play with these parameters. Let's do 50. Why is the trigger being so stupid, though? Condition rising. That's pretty good. Let's try auto. Let's try falling. Rising. It has a hard time with rising. I think that's probably its... But this is pretty good. So we want to measure... So wait, can I just pause? Stop. Okay, and then I can click and... How do I annotate something? Quick measure vertical, quick measure free. So I want to... Delta X, 83 microseconds. Oh, it's 10 kilohertz. Okay, so that's too high to hear. So if we raise the resistance, so we try to put one of these 1M. Let's do some experimenting. Oh, it's so good to be back in California, in the sun, just Feel like you can take on the world. Okay. It's 100K. 2K. Fuck, man. I could have sworn I saw 1M on here. I'll put them all back in a second. Oh, here's the 1M. All the potentiometers are downstairs. Luckily, I also have some trimmers, but I feel like I'll probably still have to buy more. Alright, so now what we're going to do, let's unplug just in case. Fuck, I'm an idiot. Oh, God. Resistor chart. I'm literally so stupid. Okay, I don't know what these two bands on the sides are. I'm pretty sure that this is just black, black, orange. No, that doesn't make sense. Oh, it's brown, black, black, orange. Yeah, that makes sense. Brown, black, black. No, that's not right. Thing is, this thing has 5 stripes on it. Okay, so yes, we got brown, black, black, orange, brown. Is that true? And where the frick did I put this one? Brown, yeah, brown, black, black, yellow, brown. Okay, this one. All right, so we're gonna unplug this guy. And we're gonna replace it with this 1 mega ohm. Okay, so our original frequency was 10 kilohertz or 11 kilohertz, which is like not inaudible, but like excruciating. Way too high pitch. So now what we want to do is we're going to plug this back in. Okay, we want to run. See, does it get a trigger? Let's zoom out a little bit. Okay, now we can stop. Zoom out. Oh, shoot. Okay. Run. Stop. Zoom in. We want to change this to here. To oh, shit. Oh, I see what's going on. Okay, hold on. No, stop. Okay, so now that's, yeah, so that's 10 times less. So this is more in the audible frequency because we 10x'd the resistance. So we should see a 10x decrease in frequency. So that's good. Okay, now we can cool. Let's see, what else do we have to do? We have to finish this though. Maybe I should do the transistor part now. The thing is, I don't have a speaker. It's really annoying. And I really want that spectrogram thing to work too. If I just pull that up, does that just work? Like with the current sample? Oh, it does. Why isn't this in hertz though? I hate that, dude. Is spectrogram what I'm thinking of? Oh, wait. No. Yeah, it makes sense that there's harmonics because it's not a sine wave. So it does make sense that there's multiple peaks, sort of. But I don't know if I'm reading this right because this is like like what is this? Alright, I think I'm gonna make some food. It does not look like it's going to rain, so I don't have to like freak out about that, even though I'm paranoid about it. The natural light thing kind of makes it beautiful. And the sound of birds. Now that there's no trash cans, I might remove this background noise thing, because I think it's cool to hear the sound of outdoors while making electronics. So we're going to disable the noise suppression. They can hear the birds. Cool, cool, cool. Okay, I guess I'll be back in like 15 minutes. Alright, I'm gonna make some food. None of this is gonna blow away, but I'm worried about it. Blowing away in the wind. They always make these resistor bags so small. It's like, just make them easy to get out of here. Actually, this one's probably big. This one's kind of big enough. Need to get my phone charger. My phone is... Oh, shit. Okay. Let me get my phone charger. Alright, we'll do the tuning in a second. Now it's time to make food. Charging. Everything's set up. Okay. I'm in California. I'm in California. See the steam coming off these beautiful eggs? Toasting eggs. I'll eat here. Ooh, actually, should I do that? It's kind of a hype thing. Alright, so now I need a new scene though. I need a scene with window and not this. So let's duplicate this and say window, face, no overhead. And then we just take this guy and delete it. Delete. Cool. Now we can go to YouTube. Do I have desktop audio on? Yeah, I do. Nice. Oh, I forgot to get a napkin. It's good to be home. This is delightful. And my my radio comes today too. I thought series resistors add. Oh, LED series. All right, I'll be back. Oh, so I put that in the recycling bin. Oh, okay, good. California, hey. I want to watch the kick drum one.
Then slow not only make our kick a pain to build, but also the initial punch that you'd expect from a real drum. Traditionally, you'd emulate that by manipulating the pitch alongside the volume, starting off quite high and then quickly dropping towards a steady bass frequency. All right, this is beginning to sound quite serviceable. So let's think about how we could implement these blocks in our circuit. In an ideal scenario, we'd want to use a full-blown VCO as our oscillator, so we can precisely manipulate its pitch via a control voltage coming from an envelope generator. Next, we'd need to add a proper VCA and yet another envelope generator, which in combination would allow us to shape the signal's volume curve into the aforementioned quick burst. Now, the problem with this approach is that each of these circuits is plenty complex on its own. Throw 4 of them together, and you've got quite the behemoth of a schematic. This would not only make our kick a pain to build, but also hard to analyze and relatively expensive. So we should probably think of an alternate approach. Thankfully, the people working at Roland in the 70s were faced with the same issue, and they came up with a couple really clever shortcuts and hacks that we can borrow. Basically, they found a way to smash a pseudo-VCO, VCA, and envelope generator into a single block made from just a handful of components. The basis for that block is this little circuit consisting of just 1 op-amp, 2 resistors, and 2 capacitors. Together, they form a strange sine wave oscillator that needs to be kickstarted by a voltage pulse to actually oscillate. And even then, it won't continue oscillating like other oscillators do, but quickly drop in volume and eventually fizzle out completely, which isn't great for most scenarios, but ideal for ours. So let's look at how this works. We'll assume that the voltage at the op-amp's non-inverting input quickly jumps from 0 to 1 volt. Now, to reach a state of balance, the op-amp will try to push the voltage at its inverting input up to 1 volt as well. For that, it'll increase its output voltage to 1 volt. Initially, this will work just fine, since that voltage pushes straight through the 2 capacitors and reaches the inverting input that way. But because there is a resistor to ground between the 2 caps, we'll see current drain out from the first capacitor, which means that the voltage applied to the second cap, and subsequently the inverting input, will drop. To compensate, the op-amp will raise its output voltage. But as it does that, even more current is squeezed out of the first cap, forcing the op-amp to push even harder. And this would continue until the op-amp runs into the upper supply voltage, if it weren't for the bridge resistor down here. Because as the op-amp pushes harder and harder, that resistor allows a small current to charge up the second cap from the other side. At some point, this process will add more voltage on the left as we lose on the right, causing the whole mechanism to kick into reverse gear. Now, the op-amp will start dropping its output voltage to try and course correct. Only problem is that this will pull current out of the first cap, and subsequently up from ground, increasing the voltage between the 2 caps and also at the inverting input, which forces the op-amp to reduce its output voltage even further. Eventually, we'll again reach a tipping point where the whole mechanism reverses. Only this time, it'll be at a slightly lower output voltage. And that's because with every charging and discharging cycle, we lose a bit of the momentum we initially put in. The circuit behaves kind of like a pendulum that way. And so the output it produces is a sine wave swinging around the non-inverting input voltage with a steadily decreasing amplitude, which should already sound pretty kick drum-ish, if the frequency is low enough. To make sure that it is, we have to choose the right combination of capacitor and resistor values. This is a little tricky, since all of those values influence both frequency and decay at the same time. In the original 808 bass drum schematic, Roland used a 1 megaohm bridge, a 51K resistance to ground, and 2 15 nanofarad capacitors, giving them a 50 Hz oscillation frequency with a really quick decay. Let's use those values as a starting point. To be able to actually trigger the sound, we'll then add a quick and dirty push button connected to the positive rail on one side and the op-amp on the other. Because the oscillator needs enough room to swing, we'll have to divide the supply voltage down. For that, we'll simply insert a 100K 14K voltage divider at the non-inverting input. To test this out, I've already set the circuit up on the breadboard. Before I push the button though, I recommend that you plug in some headphones. You might not hear much otherwise. Ready? Here we go. As expected, we get a quick low-frequency bump. Great. Though you might have noticed that we get a second bump when I let go of the button. What's up with that? Well, as we saw earlier, the oscillation is triggered when the voltage at the non-inverting input changes, and the op-amp struggles to charge or discharge the second cap to that voltage. So it makes sense that we get a second bump when we drop the input voltage. This is not ideal though, because now we'll try to control our kick with a sequencer that sends out a gate signal. That gate will go high for a while before it drops back down to ground level. This gives us 2 separate kick hits when we'd only want to hear 1. Bummer. So what can we do about that? Simple. We'll shorten the gate so much that the 2 separate kick hits blend into one and the same. For that, we'll set up a little circuit known as a gate-to-trigger converter. It consists of 2 distinct sections. First, a high-pass filter with a pretty steep cutoff frequency. And second, an op-amp-based comparator. Here's how it works.
A high pass.
When we apply a gate signal to the input capacitor, we get a voltage spike on the other side that quickly dies down as the cap charges through the 39K resistor to ground. For the split second this spike crosses its threshold voltage, the comparator will then push out an extremely short 12 volts gate, also called a trigger. Those 12 volts are then scaled down to around 1.4 volts by the voltage divider at the kick's trigger input. You'll notice that there's also a diode pointing up from ground at the op-amp's non-inverting input. This is necessary because some op-amps will glitch out if they read a very negative input voltage in this scenario. This is an issue because once the gate goes low, we'd normally see a big negative spike as the capacitor discharges. The diode mitigates that by allowing the cap to discharge instantly. Great, there's just one more issue left to solve with this setup. During the comparator's low state, it'll set its output to minus 12 volts, simply because that's what we give it as a low supply voltage. This is not ideal, because remember, our oscillator will swing around the voltage we apply to the non-inverting input. For audio signals, that voltage should be 0 volts, ground level. So how do we fix this? Simple, by placing a diode after the comparator's output. This way, the trigger can pass through, but the comparator's low state is blocked, and the voltage gets pinned to ground level via the voltage divider instead. And here's how this works out in practice. I'm feeding the sequencer's gate output into the gate-to-trigger converter, which I've then hooked up to the oscillator's trigger input. And yeah, we now get a single kick hit instead of 2 per gate. Great. Next, let's try and mess with the oscillator's pitch. As I said before, this is a little tricky, since all of the component values in the feedback path influence both pitch and decay at the same time. That said, varying the resistance to ground is probably our best bet, since it affects the pitch much more noticeably than the decay. So let's replace the 51K resistor with a 100K potentiometer and see how we fare. Right now, I've got the potentiometer set dead in the middle, so we get roughly the same pitch as before. Next, let's see what happens if we turn the knob. As expected, we can vary the pitch over a pretty wide range. Now, for our kick drum, it makes sense to restrict that range to the lower frequency spectrum. To do that, we just have to put a baseline resistance in series with our potentiometer. With a 10K, the highest possible pitch is around 110 Hz, which is bordering on tom territory. And yeah, that works as intended. Great. With the pitch sorted, let's talk about the decay. Right now, it's way too short, so I'd like to make it a good deal longer. Unfortunately, this will be a bit more involved than changing the pitch. That's because in order to keep the oscillation going for longer, we either need to reduce the amount of momentum we lose during each wave cycle, or find a way to add some back in. To try and do the former, we'd need to increase the value of the bridge resistor, because as a rule of thumb, the relation between bridge and resistance to ground determines how much momentum we lose per wave cycle. If they're close to the same value, you won't get any oscillation. If they're orders of magnitude apart, you get a relatively long tail. Only trouble is that increasing the bridge resistance will also lower the pitch, and there's a hard upper limit for the maximum decay we can squeeze out of this. Since we're already pretty close to that upper limit, and it would be great if the pitch stayed the same, I think we should skip this approach and focus on the other one, adding momentum back in. To do that, we'll set up an inverting buffer and feed it the kick's output. Then, we'll take the buffer's output and connect it to the node between our two capacitors through a big resistor. Here's how it works. We'll imagine that we've just triggered the kick, which means that the output voltage is rising. Like before, this will push current out of the first capacitor. But unlike before, we also actively pull current out via this newly added second path. That's because the inverting buffer's output voltage will always be the inverse of the kick's output voltage. So as the voltage pushing against the first cap increases, the voltage pulling at it from the other side decreases in lockstep, which in turn decreases the voltage at the inverting input, forcing the kick to push even harder. And of course, the same idea applies in reverse when the kick's output changes direction. Then, the inverting buffer will push against the caps, exaggerating the downward motion of the kick. We're basically applying positive feedback to the system, which, with these resistor values, will keep the oscillation going indefinitely without altering the pitch. And here's how this pans out on the breadboard. That looks like a pretty stable sine wave to me. Since we do want that oscillation to die down over time though, we'll need to dial back the amount of feedback we apply. For that, we'll simply add a control that allows us to reduce the inverting buffer's gain. That gain, in case you don't know, is set by the relation between the input and the feedback resistance. If the feedback resistance is smaller than the input resistance, the gain drops below 1, and vice versa. So we could simply replace the feedback resistance with a potentiometer like this. And while it does work, there is a small issue here. Setting the decay feels very uneven, because it abruptly flips from short and punchy to super long. Why is that? Well, it seems like the relation between the inverting buffer's gain and the amount of decay we get is exponential. So as we change the resistance linearly, the decay changes exponentially. To counteract this, we could switch our linear pot for a reverse logarithmic one, which would cancel out the exponential behavior. Unfortunately, that type of pot can be difficult to find. Lucky for us, we can fake a reverse log potentiometer if we simply put a big linear pot in parallel with the original 47K resistor. Because of the way those resistances will interact, the end result mimics a reverse log curve quite convincingly. And indeed, dialing in the decay is now much smoother. Alright, so that's the decay down. Our kick is starting to take shape, but there's one essential element still missing. The initial punch you get from a pitch envelope. Now to get there, we need to modify our design so that the kick's pitch can be manipulated using a voltage. But doing this cleanly would be quite involved. Thankfully, there's another quick and dirty hack we can apply here. Remember how we discovered that the resistance to ground between the two capacitors here determines the oscillation frequency? That was because the faster current can be pushed out of or pulled into the capacitor on the right, the faster the whole mechanism will swing. So if we had a component whose resistance can be controlled with a voltage, we'd be golden. Unfortunately, that component doesn't really exist, at least not in an ideal form. So we'll have to make do with a compromised version. And the most widely available compromised version is probably the good old NPN transistor.
NPN
On paper,
transistor.
it sounds like it does exactly what...
Okay. Alright. Yeah, I'm gonna go on a hike, which is sick because I haven't been on a hike in forever. I want to get some slides because then I can wear socks. Alright, so what did we do? We built, so we're gonna switch over to windowed small, no, we're gonna overhead. So we built this circuit, which is a voltage controlled oscillator, except it's not voltage controlled, it's just an oscillator. Why is it not focusing well? Stop. Look at that, Dumbo. Well, anyways, and then what we did is we looked at this program called Waveforms, which controls this digital oscilloscope that I got, which is super cool. Super cool. And we played around with it, and then that's it. And we'll be back, I don't know, in a few hours to continue. Okay, bye-bye.